Okay, so we're going to break up the lecture on statistical validity into 3 parts. In this part, we'll be talking about false positive and false negative errors, which we already learned a bit about in the lecture on null hypothesis significance testing. So as a reminder, when we're talking about statistical validity, as always with validity, we're talking about the validity of a claim or an inference, not the validity of a method or technique. So here we're talking about, are your statistical conclusions valid? If you're claiming that you observed an effect, that it's real, is that valid? So as a reminder, there are 3 different kinds of statistical conclusions we might make in the framework of NHST. We might reject the null hypothesis and say that we did observe something, we think there's something there, and the threat here is that this might be a false positive. We could, although we're not supposed to in NHST, conclude that the null hypothesis is true and there's nothing there. Again, technically, we're not supposed to draw this conclusion in NHST, but people do. And the threat here is a false negative, that you're wrong, there actually is something there. And the third possibility is that we can't tell whether or not there's something there. We don't know. We can't reject the null, but we don't accept it either. And as I mentioned, often this slides into accepting the null hypothesis. If we look and we don't see anything there, we're supposed to just stick to, I don't know if there's something there or not. But often people slide into thinking, oh, well, I didn't see anything, so there's nothing there, accept the null hypothesis. And so the threat here would be a false negative. Again, if you say, I didn't see anything, therefore there must be nothing, you could be missing something that's there. So let's take a second here and think about which of these we think might be most likely to make it into the published literature. So a researcher detects something, might be real or might be a false positive. Is that likely to make it into the literature? If they detect nothing and they either conclude, yep, there's nothing there, or we can't tell if there's something there or not, you might already have figured out that those last 2 are less likely to get published. People are less interested in publishing findings of we discovered nothing, or we don't know if we discovered something or nothing. And this is called publication bias. This is the fact that null results, negative results that are either ambiguous, we can't tell if there's something there or not, or we found nothing, those results are less likely to get published for a number of reasons, both on the part of researchers being less likely to want to publish them and journals being less likely to want to accept them for publication. And this is borne out in data looking at what proportion of findings in different sciences report a statistically significant or positive result, report a discovery. We did find something there. So this graph shows you across a bunch of different sciences what % of the published findings are significant or positive results. And it's a little blurry, so I'll explain it. Each bar is a different scientific field, and the x-axis on the bottom goes from 50% to 90%, and some of the bars even cross the 90% bar. So what you can see is that all of the fields listed here, at least 70% of the published findings are positive or significant. And towards the bottom, those fields at the bottom are where more than 90% or around 90% of the published findings claim a positive discovery, that there is something there. And psychiatry and psychology are at the bottom, but they're very close to several other fields: material sciences, pharmacology, clinical medicine, biology and biochemistry, economics, molecular biology, immunology. All of those are well above 80% of the published findings are significant or positive. So that tells us something. We're not seeing a lot of negative results. We're seeing overwhelmingly lots and lots of positive results. So that means that out of these 2 potential types of errors, we're at much greater risk in our published literature of false positive errors. There's not a lot of negative results, so there's not much risk of false negatives. It's the positive results that get out there and get spread. And so those can't be false negatives. They could only be true positives or false positives. So out of the 2 types of errors, if we're looking at the published literature, we should be more worried about false positives because there are so many positive results. So this has led to what's sometimes called the replication crisis in psychology, the realization that a lot of our positive results might not be true positives. There might be a greater proportion of false positives than we might be comfortable with. And what exactly the right proportion is up for debate. So maybe it's okay if 10 or 20 or maybe even 30% of our positive results that are out there turn out to be false positives. Science is going to make mistakes. That's normal. We shouldn't be completely risk averse. We should be comfortable with the fact that some of our discoveries won't hold up. But one concern is that it's actually a lot more than 10 or 20 or 30%, that many of our positive findings are not as sound as we think they are. And this has made the news. You might have heard about psychology's replication crisis. And it's actually now spread with the realization that this is not specific to psychology, that many, many fields publish overwhelmingly positive results, and that we should be concerned about false positives in other fields like economics, but even cancer research, medical research, the social sciences, etc. So this is a concern for any field where the vast majority of published findings are positive results, and especially when there's not enough attention to statistical validity, like we'll talk about in the following lectures, to following up and making sure those are true positive results most of the time and not false positives. Okay, so how worried should we be about false positives? You might think, well, NHST has error control built in. We talked about this in a previous lecture, that in NHST, when we're in this left world where the null hypothesis is true, because we've set our critical p-value, our alpha, to 5%, that means we're only going to tolerate a 5% chance of a false positive error when the null hypothesis is true. Now, first of all, that's only true if we follow the rules of NHST, and we don't always follow those rules. We'll get back to that in a second. But even more fundamentally, there's no guarantee that only 5% of all significant results are false positives. Here, 5% is the percentage of results in that left column. When the null is true, 5% of the time we'll get a false positive, 95% of the time we'll get a non-significant result. But the proportion of positive results that are false positives is a different percentage. It's the percentage of false positives in this bottom row. This bottom row represents all of the times we do an experiment or a study and we get a positive significant result. And most of the literature, the published literature, is in this bottom row. 90% plus in psychology and in many other fields of the published literature is in this bottom row. So what we really want to know is what percentage of the findings in this bottom row are false positives. And that is not necessarily bound by alpha. There's no guarantee, even if you follow all the rules of NHST, there's no guarantee that this percentage will be less than 5% or it could be anything. It could literally be anything, even 100%. So let me demonstrate how it could be 100%, even though I'm not at all claiming that it's 100% in any field. But just to show that there is no upper bound on what that percentage could be within the rules of NHST. So let's imagine a world where researchers are really, really terrible at coming up with research hypotheses. So they keep coming up with research hypotheses that are wrong. So in every study they do, actually the null hypothesis is true. So we're always, always, always in the left world. So in that case, even 1 in 20 of our studies that we do will be significant just by chance, because we've accepted this 1 in 20 chance, 5% chance of a false positive when we're in that left world. So we do 20 studies, one of them is a false positive. But let's imagine that we're not really paying close attention. We don't know that we live in the left world all the time because we never know which world we're in. So we think, oh, maybe we're in the right column of the table right now when we got a significant result. Maybe it's because there really is an effect. We can never rule that out. It's possible. So we trust that finding. And let's say we do that over and over again. 1 out of 20 of our studies is significant. And each time we convince ourselves that that's because, in this case, the effect really is real. We live in that right column. And we take all of those significant effects and publish just those. So then the published literature would be all significant effects, all positive results, and 100% of them would be false positives. So theoretically, it's possible for that false discovery rate, the proportion of positive significant results in that bottom row that are false positives, to be up to 100%, even if we follow the rules of NHST. But okay, that's not what's actually going on, because if that were happening, we would have to run 20 studies for every one that was publishable, every one that was significant. And that would be very slow and hard, and we'd probably notice that we have to run 20 studies just to get one to work over and over again. So I would argue that there's another piece of the puzzle that's producing false positives, not just bad luck, an extreme result by chance, but that researchers are doing something to turn some results that should be in the top row, should be negative results, we should be fail to reject the null, into statistically significant results. So when there's no effect, the false positive rate should be 1 in 20, 5%, when we're in that left column where the null is true. But it's very hard to publish non-significant results, and they're much less interesting. So we're quite motivated, without really realizing that's what we're doing, to make a positive result out of a study. So to get the study to help us discover something so that that time wasn't wasted, so that we make sure we're not missing anything, there's a lot of incentives and motivation to find a positive or significant result. So we find different ways to make things that might not have been statistically significant originally into a statistically significant result. And that increases the false positive rate, the type 1 error rate, from alpha, 5%, which is what it should be, we break the rules without realizing what we're doing and increase that false positive rate up to maybe 7%, 10%, 50%, or even more. So there are demonstrations showing that you can very easily, inadvertently, raise your false positive rate when the null is true to something much higher than 5%, maybe even 60%. And this is called informally p-hacking. You're hacking your p-value so that you can get a significant result. That sounds very intentional and bad. I don't mean it in this like scientist sitting there thinking, how can I get my p-value down? It happens quite naturally for reasons that are not so pernicious, not so evil. And we'll talk a little bit about how that happens. So what that means is that as scientists, we might do a study where we should land in the top row. We should get a non-significant result that makes us say, oh, I don't know if there's something there or not. I couldn't reject the null. But through various techniques that we've learned that we don't understand the consequences of, we push those results down to the bottom row. That's p-hacking, hacking the p-value till it gets down to p less than 0.05. So we'll discuss that more in the next lecture.